A single ChatGPT query uses about 10 times more electricity than a Google search. That sounds small. It isn't, when multiplied by 2 billion queries a day. Add to that image generation, video, and agents that run for hours without stopping. The result is one of the fastest growing electricity loads in modern history. By 2030, the world's data centers will consume as much power as Japan does today. Most of that growth driven by artificial intelligence. In this video, I will present the numbers behind the energy cost of AI, the bottlenecks to its expansion, and the trade-offs. Let's look at the numbers. In 2024, data centers consumed roughly 415 terawatt hours of electricity. That is about 1.5% of global electricity use. For context, 415 terawatt hours is more than the entire annual electricity consumption of the United Kingdom. This number has been climbing fast. Data center electricity demand grew 12% per year over the last 5 years. In 2025 alone, it surged by 17%. That is more than 5 times the growth rate of global electricity demand overall. The IEA's base case projection is clear. By 2030, global data center consumption will roughly double to 945 terawatt hours. By 2035, it could reach 1,300 terawatt hours. To put that in perspective, if data centers were a country today, they would already rank among the top 10 electricity consumers worldwide. By 2030, they would sit between Japan and Russia in 5th place. The driver behind this curve is not cloud storage nor video streaming. It is AI. The increase in AI utilization requires significant hardware changes. The shift is from CPUs to GPUs. While CPUs handle tasks one after another, GPUs run thousands of matrix calculations in parallel, exactly what AI training and inference need. A single H100 GPU draws 700 watts. The newer Blackwell GB200 draws 1,200 watts. A traditional server rack draws between 5 and 15 kilowatts of power. An AI server rack is a different machine entirely. A rack of 4 NVIDIA DGX H100 servers pulls roughly 40 kilowatts. A rack equipped with the new machines draws 120 to 140 kilowatts. This density changes everything. Air cooling can no longer keep up. Operators are switching to liquid cooling. Power infrastructure is being rebuilt around the rack. A single large AI training campus now requires between 100 megawatts and several gigawatts of dedicated power. OpenAI's Stargate Abilene campus is 1.2 gigawatts. Meta's planned Hyperion site in Louisiana targets 5 gigawatts, enough electricity for roughly 3.5 million homes. Now the workload itself. There are 2 phases to AI energy use: training and inference. Training is the upfront cost. It involves thousands of high-end chips running continuously for weeks or months. A single frontier model can consume gigawatt hours of electricity to train. Inference is the running cost. It is what happens every time you send a prompt. Inference is smaller per query, but it never stops. Estimates suggest 80 to 90% of AI computing power now goes to inference, not training. The growth is concentrated in a handful of countries. The United States already accounts for 45% of global data center electricity consumption. China accounts for 25%, Europe 15%. Together, the US and China will produce nearly 80% of projected global growth through 2030. US data centers consumed about 4.4% of national electricity in 2023. By 2028, that figure is expected to reach between 6.7 and 12%. And by 2030, US data centers will consume more electricity than all American energy-intensive manufacturing combined, including aluminum, steel, cement, and chemicals. The strain is local, not just national. In Virginia, home to the world's largest data center cluster, these facilities already use 26% of state electricity. Northern Virginia has effectively halted new data center permits as grid operators issue formal capacity warnings through 2028. This is the central tension. AI workloads are growing globally, but are straining local grids. Where does all that power come from? Coal currently provides about 30% of data center electricity globally, a share heavily weighted toward China. Renewables, wind, solar, and hydro, supply roughly 27%. Natural gas and nuclear make up most of the remainder. Over the next 5 years, renewables are projected to meet nearly half of additional data center demand. Natural gas and coal supply most of the rest. Nuclear is expected to play an expanding role from the late 2020s onward. The hyperscalers are signing power deals of an unseen scale. Microsoft signed a 2-gigawatt nuclear agreement with Constellation Energy through 2040, the largest corporate nuclear contract in history. Amazon secured 1.5 gigawatts of dedicated solar in Texas. But grid connections take years to build, so many operators are also turning to on-site natural gas generation, particularly in the United States, to avoid waiting on transmission upgrades. To put AI's electricity usage into perspective, by 2030, data centers are projected to account for about 3% of global electricity consumption. They will drive roughly 8 to 10% of total electricity demand growth this decade. That is significant but not catastrophic. For comparison, electric vehicles are projected to add 838 terawatt hours of demand by 2030. Air conditioning will add 651, and industrial sectors almost 2,000. Data centers add only 530. The energy efficiency of data centers is also increasing fast. The energy required per AI task is falling at what the IEA calls a rate unprecedented in energy history. The question is not whether AI will use all power available. It will not. The real story is local strain, infrastructure lag, and resource trade-offs in specific places, like Northern Virginia where load is concentrated. In these cases, transmission and production cannot keep pace. The next decade will be defined by how quickly utilities, regulators, and operators can resolve those constraints. AI's energy footprint is manageable. Whether we manage it is a different question. The global energy system is complex. Your understanding of it doesn't have to be. Subscribe to learn something new every week.